Okay, well, good morning. Is this recording?
Yes.
Okay. Now, I just want to make a few comments about the midterm. So I'm quite happy with the grades. I mean, I think that if you look at the distribution of grades, it makes a nice Gaussian distribution. So it means that the exam was spot on. It wasn't too difficult, it wasn't too easy. It was just right. Any questions or comments about that? For those of you that didn't make it, it's not a problem because you still have the opportunity to make up the, let's say, term grade by, boosting your average with the tutorials, right? Remember, I'm only going to pick the top 4, so that means you can, in principle, get a very high grade that counts 20%, and then, yeah, you're going to the exam with quite a comfortable margin to pass the course. So I don't think it's any problem. Yes.
What was the percentage of the midterm?
35%.
35. Okay.
So 35% for the midterm, 20% for the tutorial, and 45% for final. Okay, today we're going to be talking about acids and bases, and I mean, I sort of realized in the tutorial the other day that there is a substantial number of people that just haven't done this at all in high school, which was very surprising for me because, honestly, like I said to my tutorial group, some of the stuff we were talking about is stuff that you really should have done in the 10th grade, honestly. So, in light of that, it makes no sense to go to advanced topics if we haven't covered the basics. I'm forced to start from zero. I think this makes more sense because it makes no sense for me to start with a Henderson-Hasselbalch equation if you don't know the basics. So I'm starting from the absolute basics, from zero. And most of what I'm going to be doing today, unfortunately, is high school chemistry because there's a number of people here that haven't done it. I don't understand why, but anyway, that's the way it is and it's not your fault. So I've decided to just go back to zero, and we will start off with absolutely the fundamentals. Okay, so where are we in chemistry? We're talking about acids and bases, and we encounter these every day. Most of you, if you had a shower this morning, used some product that had some pH, perhaps shampoo, soap. If you drink too much wine, like I do, sometimes you get stomach problems and you have to take antacid tablets. This is controlling the pH of your stomach. So I always have those in my house, by the way. And of course, acid rain is an issue as well, right? So this is all about pH, and that's what we're going to be talking about today. Right, so this is sort of the overview of what we're going to be discussing today. Quite a lot of topics. We're not going to be doing the common ion effect today. I've taken that out. But what's very important is buffers. That's sort of really a very important topic for today's lecture. Now what we have here is basically just some examples of different household products on a pH scale. And you see on the left here we have the pH from 0 to 14. 7 is neutral. Pure distilled water has a pH of 7. And you can see we've got some stuff that is acidic. For example, there's the wine. Milk is slightly acidic. Tomatoes, and of course citrus. Bread, you can see, is also slightly acidic. And then we've got stuff that is slightly basic. Eggs, for example. And here's a leg sticking up. I don't know what that's supposed to be. Anyway, maybe some products for hair removal or something. I really have no idea what this is, but yeah, it looks quite interesting. Okay, so what you see on the right here is actually another sort of scale, and we're going to get to this today. Okay, we're going to get to this today. What is the scale on the right, and what is the scale on the left, and what is the mathematical relationship between the two? Okay. Now let's look at some models of acids and bases. Now, really, there was a tradition in Scandinavia of trying to understand acids and bases. And the first guy that came along and proposed the theory of acids and bases was a guy with the name of Arrhenius. You see, this is around the turn of the 20th century when this stuff was done. And what Arrhenius basically said, he won a Nobel Prize for his efforts in 1903. He said, well, it's very simple. An acid is a substance that is a source of H pluses, and a base is a substance that is a source of OH minuses. In other words, if you dissolve it in water, an acid's going to liberate H pluses, and a base OH minuses. And that was his theory. And if you mix an acid with a base, you're going to get a neutralization, and you're going to end up with basically water, because the H plus and the OH minus are going to associate to form water and sodium chloride. An acid plus a base forms a salt plus water. I mean, that's really like 6th grade chemistry. Okay, so that's basically what he said. Very simple and elegant theory. And H plus and OH minuses come together and form water. Now, this theory had some problems because there are some substances that are basic that have nothing to do with OH minuses. For example, ammonia. Ammonia is a base, but this theory doesn't explain it. So this theory is very limited insofar as it explains acids and bases bearing OH minuses and H pluses. So another guy came along, well actually two guys, Bronsted and Lowry. Again, you can see Scandinavian, Bronsted. And he defined it differently. So in order to take this shortcoming of the Arrhenius model into consideration, he said an acid is a proton donor and a base is a proton acceptor. Very simple. So that's the Lowry-Bronsted model, the Bronsted-Lowry model. Here we have an example. That is acetic acid, that's water. If we look at the dissociation of acetic acid and water, well, we can see that this theory in operation. So this is acting as an acid, because if you look at the forward reaction, the acetic acid is donating a proton to the H2O, and what we're left with is a CH3COO minus, well, that's what's left after this proton donation, and H3O plus, the hydronium or the oxonium ion. So clearly, according to this definition, this is acting as an acid, this is acting as a base. This is a proton acceptor, this is a proton donor. Now notice, we can also look at the reaction from right to left. And if we go the other way, in other words, here, this is acting as an acid because this is donating a proton to this group here, and we go there to the other side. Now, what we call that is the notion of acid-base conjugate pairs. So, if we go from left to right, this is acting as an acid. This is its conjugate base. From left to right, this is acting as a base because it's a proton acceptor. And this is its conjugate acid. So this idea of acid-base conjugate pairs is very important, okay? All right, and we can play the same game if we look at the reaction the other way around, in other words, from right to left. Here, in this case, this is behaving as an acid, clearly. It's donating a proton to this here. This is its conjugate base, and this is the base of this conjugate acid, and so on. So acid-base conjugate pairs, right? Now, here we have, as we said, the Arrhenius model did not explain very well bases that do not have OH minuses, for example, ammonia. And here we can see that the Lowry-Bronsted model does so particularly well. So here we have ammonia mixed with water or dissolving in water. Notice what's happening. In this case, we are generating an OH minus, but it's not the ammonia that's generating the OH minus. The OH minus comes from H2O, which is actually in this case behaving as a what? As an acid or a base? Yes, it's a proton donor. And what's ammonia behaving as? Obviously as a base. Because if you look from left to right, the NH3 is picking up a proton and you're forming NH4 plus, the ammonium ion, and you're left with OH minus. So in this case, this forms an acid-base or base-acid conjugate pair, and this, a base-acid conjugate pair. All right. And the point to remember is that typically these reactions are reversible and at equilibrium. So you can look at the situation from left to right or from right to left. Okay, we now look at the equilibrium constant. Now, we looked at this some time back. We looked at this a few lectures back. We discussed Kc, the equilibrium constant. If I were to write an equilibrium, a Kc expression for this, what would it be? What would the equilibrium constant expression be for this reaction here?
So the concentration of OH minus multiplied by the concentration of NH4 plus divided by the concentration of NH3, and you usually leave out water.
Right, but okay, we usually leave out water, but if we're talking about a classical Kc expression, the concentration of the water would be included as well, right? Remember that? No, okay, so that, yeah, that should be Kc. That's the expression we get. Now, in the context of acids and bases, because the water is typically behaving as a solvent, we just whack that out of the equation. So we arrive at an expression which we call K subscript B for base, and this describes we call this the base ionization constant, and that would be the Kb expression for this reaction. So it's exactly the same as Kc, except we've just taken water out of it, right? This is just something we do. It's, let's say, convention. So if we know, so that's Kb, we can play the same game for Ka. So here we have some sort of an acid, let's call it Ha, just whatever, some generic acid. And this would be the acid-base equilibrium. We end up with, it reacts with water, it's behaving as an acid because it's donating its proton to the water. An acid is a proton donor. So if we look from left to right, this is behaving as an acid, this is behaving as a base. This is the conjugate base, sorry, so this is acid, this is base. So this forms an acid-base conjugate pair. This forms an acid-base conjugate pair. Now, we can also write a Kc, or a Kc expression for this, and a traditional Kc expression would be what?
Times A minus.
Concentration, yes.
Divided by HA. Yeah, times H2O.
Correct, that would be Kc. Now, in the context, so that should be Kc. So in the context of acid, we also have an acid, sorry, ionization constant, where like we just saw with the base, we just take the H2O out of circulation. All right, so I think you all understand that. This is just another example. Here we have acetic acid, which is the acid. This is the conjugate base. The acetate anion, and you can see by using this definition of proton donor and proton acceptor what's actually what here. Are there any questions? These are important fundamental groundstones. Just one word on the hydronium ion. We generally represent it as H3O+, right? H3O+. It's also sometimes called the oxonium ion. You can use either interchangeably. This is a very interesting species because it exists experimentally. Scientists have shown that it exists in all sorts of different weird forms. It forms these networks, and actually you have an H9O4+. These things exist because of what? What is this dotted line here? Yes, it's a hydrogen bond. Now, for the purposes of this course, we're only going to deal with this. So what it basically is it's a water molecule with a proton attached to it, an H+. Okay. So generally, we write H3O+ when we're talking about acids and bases and not just H+, because it's occurring in an aqueous solution. So there's water floating around that's going to pick up the H+, right? You're not going to have a naked proton floating around in solution, when there's water molecules surrounding it with lone pairs, they're going to just snap up that proton, and what you're going to have is that. Right, it's obviously positively charged. Right, okay. So what we basically have here, this is sort of a cluster. We have the oxonium or the hydronium ion over there, and it's basically just solvated with a, let's say, a coordination shell or a hydration shell of water molecules around it as a result of hydrogen bonding. So this is how these things sort of exist in solution, just some information. All right. I now want to talk a bit about something very important. Sorry. It is the idea of strong and weak acids. Right. Now this I find is a term or a concept that students also get confused with. That is why I want to really make sure that we iron this out. Can someone tell me? Okay, I'm going to make a statement. Right. I've got HCl, and I make a 1 molar solution of HCl in a beaker, and I make a 3 molar HCl solution in another beaker. Okay. Now, I'm going to make a statement, and I want you to tell me what you think about it. Here, in the 1 molar situation, the acid is weaker than here. Is that correct? So here the acid, in the 3 molar solution, because it's a higher concentration, it's a stronger acid, because it's a higher concentration, so it will be stronger. Is that correct, that statement?
No.
No, why not?
Because it's of the conjugation you get, not the HCl concentration.
There is a difference between concentration and strength. That's the point. People mix up strength, acid strength, and concentration. All right, exactly. So sort of you're on the right track. Basically, a strong acid is simply an acid that ionizes almost to completion, or let's say to completion in water. An example of that is HCl. Another example is H2SO4, and so on. Okay, nitric acid. It ionizes to completion. Weak acids, typically organic acids, like acetic acid, formic acid, citric acid, all these organic acids do not ionize to completion. And so if we take the Ka value for a strong acid, for a very strong acid, HCl, what would the Ka value be for HCl? Let's write down the expression. All right, for acid dissociation. All right, there it is. So, Ka, what is the Ka expression? Someone?
H3O
Plus.
A minus divided by HA.
Right. Now, if we've got a strong acid, like HCl, one that ionizes to completion, what comments on the value of Ka? Is it going to be big or small?
Well, we pay.
Sorry?
It'll be high.
It will be extremely high. For a strong acid like HCl, which ionizes to completion, in fact, if we assume a 100% ionization, it will be infinite. Because there'll be no HA left. Because it's all ionized completely. But if we have a weak acid like acetic acid, the Ka value will of course be lower. And so you can judge the strength of an acid on the value of Ka. So the higher the Ka, the stronger the acid. It's very simple. Right? And so that's a very useful metric on how we can establish the strength of an acid. Okay. All right. So here, for example, we have acetic acid. This would be a weak acid, meaning that you're going to have, in a typical situation, you're going to have some unionized acetic acid present in the beaker, right? And only some of it would have ionized. Whereas if you have HCl, let's say all of it would have ionized. Now, there's no such thing in science as 100%, but it would be 99.999% if it's a very strong acid, okay? Okay, now, fortunately for us, it's possible experimentally to determine these Ka values, and scientists have done that. And by the way, we have the same thing for bases. So we also have the notion of a strong and a weak base. Sodium hydroxide, for example, is a strong base. Ammonia is a weak base, meaning that the Kb value for sodium hydroxide will be extremely high, perhaps infinity. And or let's say 10 to the power of 10 or whatever, extremely high number, because it's ionizing to completion. Whereas for ammonia it will be much lower, because it's not ionizing completely. Okay, now, yeah. So the acid strength has basically been tabulated for us, right? And so what we have here is the acid, and this is the conjugate base. Now, the general rule is if you've got a strong acid, the conjugate base will be a weak conjugate base. If you've got a weak acid, in other words, one that is not ionized to completion, the conjugate acid will be a strong one. So for example, here we've got a strong acid, HCl. It's a strong acid. You see a strong acid is 100% dissociated in aqueous solution. All right? Strictly speaking, there's no such thing as 100%, but yeah, okay, basically, let's approximate it to near complete dissociation. These are the conjugate acids, and these are weak. So these are very weak bases, conjugate bases. At the bottom of the table, right, we can even think of NH3 as an acid, because it's got 3 protons, so it could, in principle, behave as an acid. This would be its conjugate base, NH2 minus. Therefore, if NH3 is an extremely weak acid, NH2 minus its conjugate base would be a very strong conjugate base. So that's the general rule. You know, if you've got a strong acid, you'll have a weak conjugate base, and so on. The next thing I want to talk about is the notion of an amphiprotic substance. Can someone tell me what that means?
It's a substance that
Correct. It's a substance that has the capacity to behave as a base and an acid simultaneously. Can someone give me an example?
What?
Yes, water. I mean, water is a classic example. Why? Because water, if we take water, it can act as an acid, forming OH minus, or it can act as a base, in which case it would pick up a proton. So it's amphiprotic. It has the capacity to act as an acid and a base. Okay. Here we've got some other examples. This is another classic example. This is H2CO3. And you can see here, basically, it's another classic example, right? Actually, HCO3 minus is a classic example. So HCO3 is amphiprotic. It can give up another proton. In other words, it can act as an acid forming CO3 2-, or that HCO3 minus can pick up a proton to form H2CO3. In other words, it has the capacity to act as a base. Incidentally, H2CO3 has 2 acidic protons, so we can talk about a Ka1 and a Ka2 value. All right? So sometimes you've got polyprotic substances. They don't just have 1 proton, but 2. So that's another thing that I'm sort of throwing into the mix here. We have the notion of amphiprotic substances, But we also have the idea that we can have substances that have more than one proton available for behaving for ionization. All right. Now you just mentioned correctly that water is the classic example of this, and here we see this, exactly what I've written on the board. Again, just for the sake of clarity, if we go from left to right, we can see that in this case, this water molecule is acting as a base, it's picking up this proton. This water molecule is acting as an acid, it's donating a proton. So this is so these are the conjugate, this is the conjugate acid base pair of what we have here. And if we go the other way, we can see, we can play the same game, but it's amphiprotic. Now if we write the equilibrium constant, or the equilibrium expression, for this reaction that I've written down here, it's kind of silly, but it's H2O plus H2O forms H3O plus plus OH minus. Now let's play the same game we played before with Ka and Kb. So what would be the Kc expression for this? Kc. Someone.
H3O times OH minus divided by H2O is H2O.
Correct. Or H2O squared. But because we're talking about acids and bases, and because we use it as a solvent, by convention we just take these H2Os out. And so what we're left with simply is that expression over there. In other words, the product of H3O plus the oxonium ion times, or the hydronium ion times OH minus. Now experimentally, it's been found that this value is in fact 10 to the minus 14. In other words, this product, scientists have been able to measure in a laboratory, has a value of 10 to the minus 14. In other words, since they are available, since they're present in equal quantities, it's 10 to the minus 7. Okay? And we call that Kw. We call that is another special name. We just call it Kw because we're dealing with the ion, we call it the ion product of water. It's simply the product of H3O plus and OH minus, which is a value of 10 to the minus 14, or 1 times 10 to the minus 14. Meaning that H3O plus and OH minus both has a value of 10 to the minus 7. Any questions? Okay. Right, let's talk about the pH scale. The pH is defined as the negative logarithm, base 10, not the natural logarithm, base 10 log, of H3O plus, and POH is negative log OH minus. By the way, P functions are very important in science. They appear every now and then. It's always defined as the negative log of whatever you have there. So PX would be negative log X. You know, so don't forget that. And this is just simply pH. So the reason why we use this is because if we talk about concentrations of H3O plus, we end up with these strange numbers, 1 times 10 to the minus 7. It's inconvenient to write numbers like that down. If we use a logarithmic scale, it's easier. We just end up with a nice, neat number. That's the reason why we have a pH scale, because it's a logarithmic scale, which makes it more convenient to write stuff down. Okay? Now, basically, this you should all know. I mean, if you have a pH, if you arrive with a pH from 0 to, let's say 6.9, or just before 7 is neutral, anything below that is acidic, and anything above that is alkaline. We also have a POH scale, which is negative log OH minus. And there is a very important result, and that is that POH plus pH equals what? 14. In other words, if I determine the pH of a solution, I can very readily determine the POH, and vice versa. Now that comes from the mathematics of all of this stuff. There it is. And this is something that you've all seen. Here we've got some examples of stuff we use every day. Beer, for example, has a slightly acidic pH. Vinegar, gastric juices, pH 1 to 2. That's why if you've got acid indigestion, you take antacid tablets. Literally what's going on is that there's an acid-base reaction. And typically it's some sort of a carbonate. That's why you drink bicarbonates of soda, you know, and then you feel better. So ammonia, pH 11.9, and so on. Baking soda, 1 molar NaOH, pH 14, right? Don't ever get that on your hands. And if you do get it on your hands, you'll feel it feels like soap, right? Sodium hydroxide. It's really terrible stuff to get on your hands. Okay, so let's recap what we've done up until now. We've looked at the Arrhenius model, we've looked at the Lowry-Bronsted model, we've looked at the definition of Ka and Kb, we've discussed amphiprotic acids, amphiprotic substances, substances that can act as an acid or a base. We've looked at we've distinguished between strong and weak acids and bases. A strong acid is one that dissociates to completion. A weak acid is one that dissociates incompletely. We then have the notion of a Ka value, which tells us about the degree of dissociation. Kb is analogous to that. Water, which is amphiprotic, we defined Kw, which is simply the product of H3O plus and OH minus, which comes to 10 to the minus 14, and now I've introduced the notion of pH and pOH. Okay. Here we have the sliding scale based on this mathematical relation here. Very obviously, we end up with this situation here. Incidentally, we also have something called pKa. What is pKa per definition?
The negative model of the
Correct. And we invented that for the same reason. Why? Because the Ka value of acetic acid is something like 1.5 times 10 to the minus 5 or something like that. It's an inconvenient number. But if you take the negative log of it, you end up with a nice, neat number that you can write down. So it's just